and improvise the solution.
Yes.
So if you need, I can connect you to these people.
Sure, sir.
Yeah, thank you.
Thank you, sir.
So the next presenter, we have Nikhil. Yeah. An improved and secure VSS scheme for medical images. Nikhil is from NITK, National Institute of Technology, Surat.
Sir, can you do this presentation later?
Good morning all. I will be presenting on an improved secure visual security scanning scheme for the medical images. So let's start with what is meant by cryptography. So what is the cryptography is like we all know that it uses the key to encrypt any data. So we need all key to encrypt the data, and at the decryption side also we need a shared key. So we are providing a new way, like a modern cryptographic solution to it, so which is known as visual cryptography. What it does is it doesn't require any key to be shared among the sender and the user. So like sender and the receiver. So what we will do is we will encrypt the secret image in the form of multiple shares, and that will be transmitted over the network, so that at the receiver side they only need to stack that images to get the final output. So why we need this in the medical images? So as you know that privacy is more concern nowadays, like more effective concern nowadays. So for that we need to securely transmit our data, and also whenever we are collaborating with the medical field or doctors, whenever we are asking them to give data, patient's data or something, they won't give their data like names and all that, gender and all. So this information is like private information that need not to be shared. So that's why to preserve the privacy of the patients, we need a scheme which will transmit the images over the network securely, and also it should be we should not share any keys between the sender and the receiver to transmit the images, and it should recover persistently. So what in the secret sharing, these are the many schemes which has been developed. So earlier we have proposed a progressive based visual scheme which will recover the images which are like normal images. So you can say like CCTV footage or the video camera footage or the images that can be recovered easily. But when you are concerning about the medical field, we can know that like we have tested this system on the breast cancer data set, that is histopathological images, which are very much complicated. So you can observe the images. It will have the images will be having the less it is like consistent. So correlation is like almost similar images. So you cannot get the difference between the cancerous cell and the normal cell. So for that reason, we have implemented the new improved version of the visual secret sharing by adding the super resolution part onto it. So like super resolution and visual cryptography are two different techniques. So we have combined that to give the better solution and the reconstruction cost. So this is the overview. At the sender side, sender will be having the secret medical images. He will generate the shares, and he will embed the basic information about the images into the shares. So that will be transmitted over the network, and that at the receiver side we will extract the hidden information, plus we will recover the shares by stacking it. Then we will apply the super resolution on it to get the clear reconstructed image. So it will having the we are able to reconstruct the medical images up to the 70 to 80%. So for that, for the now how to generate the shares, that is the thing. So for generating the shares, we will be like converting that images into the halftone format. So what we will do is, we will convert that image into the halftone format. So what is halftone format is basically the technology used by newspaper. So it uses the very like black and white dots only to present the images. So we will be applying these images on the color images. So for that, we will be taking RG and B channels separately to get the to generate the shares. So we will be applying the halftone technology on it. After generating halftone, we will be we will be selecting the random pixels from that. So random pixel, if it is the white, we will be having the tables which will which will pick the random values and it will convert it into the zeros and ones. All will be converted. All will be given to the algorithm and it will generate the shares. So I think I have less time, so I will not discuss the algorithm. Let's go to the outputs actually. So, like main thing what we have developed is the super resolution part. So in the super resolution part, the images which we have, we are like the low resolution images which we have extracted here, it will be used as a prior knowledge for the super resolving the images. So we will be having this recovered images using the XOR operation, that is simple XOR operation, which doesn't need any computation cost. So the solution which we are providing is cost efficient. So it will be having the multiple images. So we will be using the MISs, like multiple image super resolution on it. So after that, it will reconstruct the images. So to show the output, so these are the test images. As you can see that normal samples, the cancer samples, and invasive like carcinoma in situ, and the invasive subjects are having the similar appearance. So this type of images are seems to be very complicated to reconstruct. So what we did is, earlier we have proposed RVSS scheme, which uses the block-based which uses the block-based processing to reconstruct. So we had this artifact in that. So to resolve this artifact, what we did is, we have applied the super resolution on it using the embedded data. So what we have embedded is actual this low resolution image in it, and we have applied XOR on this reconstructed image to super resolve it. So after super resolution, you will get the clear cut images which can be used for the automatic detection. So we have did experimentation using the CAD system. So like computer aided diagnosis, for that we have applied normal feature extraction and the classification using the SVM, and the feature extraction using the DCT and the shift feature. So it has shown the relevant appropriate or say more similar results than the whatever images which are providing. So we are almost able to get same results for the original images, whatever we are transmitting. So after reconstruction, we will get the same results for the CAD system. So to conclude it, in the future work, we can have the more robust CAD system to automatically divide the cancers and detect the cancers from the cell. And we can now we are reconstructing image with 70%, and we are planning to boost that to up to 80%, and we are on we are changing our super resolution techniques. It's already implemented, so maybe I will discuss it in next workshop or something. So thank you.
Any questions? Okay, thank you, Nikhil. Before we go to the plenary talk, because I just want to make sure IoT solutions for hospitals, Aditi is here. Oh, you're here? Okay, can you load your presentation, give it to a volunteer? So by the time we have another paper, novel evaluation methodology for machine learning applications algorithm through API creation by Soumya, who is working for Philips Innovation Campus. So as a mark of celebration of ComsNet 2019, today is the last day. So in the evening after the workshop we end, we have wine and cheese to refresh ourselves the memories of ComsNet. So all of you are requested to join after the workshop.
You can use the pointer.
Hello, this is Soumya. Today I'll be talking about novel evaluation methodology for machine learning algorithms through API creation. This is the presentation overview. What this abstract of use case, coming to abstract of use case, there is a need for an API for the data scientist in order to evaluate the standards of the code and also the functionality of the feature that are part of the execution of the algorithms. So in this work reported, we'll be talking about an API termed as a score API. What do this score API do is, this will score the algorithm. So what do actually the scoring of an algorithm means? It can be a machine learning algorithm and the normal algorithm according to the requirement as well. So anything which needs to be communicated to the score API is through curl commands. What this curl command will do is, it will facilitate the transfer of files to or from the server. Simple as that. So the pre-requirements that needs to score a machine learning algorithm will be given as part of these curl commands, which will be an input to the score API. So coming to the introduction, the data scientists write and customize code for each project and experiment separately. What is workbench environment? Here we call the Health Suite digital platform as a workbench environment. What do this platform have? This platform will have the libraries which are prerequisites and the machine learning algorithms as samples, all the popular machine learning algorithms which are readily available as part of this platform, and the sample data sets which are readily available to utilize as part of the machine learning algorithms and work on. So this is Health Suite digital platform, that is HSDP. Coming to the readily available library means any machine learning algorithms will use patient's data in the form of CSV format. So the libraries what this platform will provide is, for example, read CSV. So you can just import read CSV as is without any modification and can use your CSV file as part of that library so that you can read the CSV file without coding separately for that function. And the next one would be the sample data sets. These sample data sets are the clinical data sets which are readily available with de-identification. So the de-identification means there will no have the patient's personal data. So it is readily available, which can be used through machine algorithms. And all the popular machine algorithms like deep learning and Navy Base are available as part of this workbench environment. Multi-layered platform because it will use the it uses the modular approach to save the data, code and the libraries what I mentioned as now. Here comes the picture of an API in order to ease the exchange of files through these modules. And coming to the score API, as I said, we can score the machine learning algorithms through score API. The scoring of machine learning algorithm means we can execute the machine learning algorithms the backend to the platform, where the code security comes into a picture. Here is a small block diagram. As I already mentioned, it is a multi-layer structure. One layer of the workbench has been projected over here. Data, libraries, and a code. A single layer containing the data, libraries, and code. As I mentioned, the data contains the clinical data. The libraries are predefined libraries which can be used as part of the machine learning algorithms without any modifications. The code means that all the supporting header files comes under the code. The machine learning algorithms will have an interaction with the layer of data, libraries, and the code, which can be scored through score API. Features of the platform. We can see the platform being comprises of 3 layers, that is project creation, experiment and the saving of scripts. The project creation, any number of projects can be created under the project, and any number of n number of experiments can be created. Under experiments, the scripts, the required scripts, the scripts, what I mean is the machine learning algorithms can be coded, and n number of machine learning algorithms can be coded. So workflow. Okay. There are 3 curl commands what we use here. The first curl command take care of the authentication of the person logging into the workbench. Here comes the 2 roles, that is the data scientist and the support user. The data scientist will have an access to the RStudio and the Jupyter Notebook, which are part of the platform, and he can code the algorithms using the sample data set, the sample algorithms and the libraries. And the second role comes the support user, where he'll have access only to the logs and the result of the score API. Thereby, I said the scoring of an algorithm, that is running of an algorithm backend, is a secured process where your algorithm is safe and secured. The projects and the experiments are created with the title and the brief description. This have the usage of the step 4, accessing the created project and the experiment. When you create with the proper tags and the description, the filtering of the projects and the experiment, when you have n number of projects and experiments, are easy. And saving the required script within the created experiment inside the project needs to be done. We need to follow the layered structure while you are creating the project, experiment and the script. Deploy the experiment. What do you mean by deploy the experiment is a data scientist using the platform can deploy the project, experiment and the script onto the cloud. When the same data scientist share the URL of the deployment, the other data scientist can have the access to his work in order to improve or in order to alter the work according to his requirement, instead of investing one more the huge amount of time while creating the same and same again. The application. We need the quantitative measure of success or failure of an API. The result of an API will be the understandable messages whether your algorithm has been success or fail or pending, because the algorithm will be running at the back end. You need to quantify the algorithm, you need to quantify upon the result of an algorithm, which will help in debugging the algorithm and streamline the development process. Health check of an API is very much important for any design of the platform. This API can be mainly used in the healthcare imaging industries, since there is a freedom of selecting the machine learning algorithm required according to the image that you use. And also the curl command can be modified according to the image type you use, either DICOM or Nifty or anything else. Here are the results. The result you see, when you score the algorithm, these are the kind of results you get. Either success or still the execution is pending, you get it as pending, and failed, you can see that is the failed message you get. So it helps in debugging of your algorithm. Okay, since we test, save and share the logs of this API, we get the valid feedback from the users, which will help in debugging and also the building upon the quality of the platform. And also we can also tick upon the time taken to compile the data set through the machine learning algorithms, and can work on the time without affecting the accuracy of the algorithm. And code security, since it runs at the back end, the code is safe and secured. And also, since the messages are in a readable format, the maintenance is easy. So the acknowledgements to these 2 people, and thank you.
Questions? Okay, thank you, Soumya. So next we have IoT solutions for hospitals. Aditi from DY Patil School of Biotechnology, Bioinformatics will be presenting it. Okay, Aditi, instead of Aditi, Hetvi will be presenting.
Will you walk or will you use this? Okay.
Hello, good morning everybody. My name is Hetvi Gandhi. Today I am here with my friend Aditi Patade. We both took this project in our bachelor's program under the guidance of Ms. Nidhi Sharma. So the title of our paper is IoT Solutions for Hospital. I will be covering all these contents. To introduce IoT, to simply put it, it is a point in time when more things or objects were connected to internet than people. To define IoT, it is an interconnection via internet of computable devices which are embedded in everyday objects, and it enables them to transfer and receive data. Since our background is from biomedical engineering, we took this IoT and incorporated that into healthcare systems and hospitals. Now, for our project, we concentrated on 3 major problems faced by hospitals. One is of vascular air embolism. In any regular hospital, may it be 50-bedded hospital or 200-bedded hospital, the intravenous infusion of saline is pretty common. And it gets very hectic to monitor each and every saline bottle of patients, and it gets difficult for the nurse. And the problem is that when the saline bottle gets empty, there might be air bubbles still inside that, and those air bubbles might transfer into our bloodstream through the intravenous supply. Once these air bubbles enter the bloodstream, it obstructs the blood flow and then form a clot. These clots may then enter the heart and then cause many serious complications such as cardiac arrest. The second problem which is common in hospital is hospital fire. Though it may not be common, but it is very dangerous. Mainly in a place like hospital where people are vulnerable and are in a position where they are immovable. The third problem which is encountered by hospital is excessive energy use. Apart from the energy usage for the medical equipments and other necessities, energy consumption is more in the lightings and fans of the hospitals where it is not needed. We can conserve this energy and use it in more important medical equipments. For the solution of vascular air embolism, we came up with a prototype of a saline holder where you can hold the saline bottle. In this saline holder, there is a IR sensor which will notify the nurse when the saline level is about to get empty. Now, the principle of IR LEDs is that one IR LED acts as an emitter circuit and the second one acts as a photodiode circuit. When the emitter circuit emits IR LEDs, the photodiode receives it and gives output in the form of voltage, and this voltage is in proportion to the IR light which it received. The features of this saline holder is that alert is sent to the nurse before 10 to 5 minutes of saline getting empty. Hence, it makes it easier for the nurse to immediately change the saline bottle before any problem. Air embolism is prevented at an initial stage. The rigid holder makes sure that the bubbles are not generated in the bottle when the patient is being transported from one room to another. The light weight of the holder and small size of the sensor makes it suitable for the hospital environment. Now, for the hospital fire problem, we came up with a model which incorporated a microcontroller and a gas sensor. This gas sensor senses the gas molecules emitted by the fire at an earlier stage. When the gas sensor senses that those gas molecules, it gives an alert to the user that there are chances of fire, and it alerts the hospital staff. Features of fire solution, fire detection are: it responds to the smoke within few seconds. It sends visual data, that is, in our case it was red LED, as well as notifications to the user. It is sensitive to explosive gases like LPG. Therefore, instant reaction can be expected in case of gas leakage. For the third solution, we made up a model of motion sensor. Whenever a motion or human movement is detected in a room, the lights or fans will switch on immediately, and whenever there are no human beings inside a room, it will switch off automatically, hence conserving the energy. It doesn't need manual checks, reduces the workload and therefore the human labor. The used energy can then be shifted to operate other critical care instruments. For our IoT solutions, we used IoT platform Blink. So we were successful in achieving the notifications in the real time. For vascular air embolism, after doing experiments, we obtained a threshold value when the saline is about to get empty. So you get the notification at the real time. For fire alert, same, we interface the IoT platform Blink with the fire sensor, and here also we achieved a threshold value which was calculated by experimenting the sensor in presence of certain gas molecules. A notification was received to the user and alerting about the fire in the hospital. For future scope of our project, the motion sensing circuit and fire detection model is developed considering the environmental factor and patient safety respectively. Since 11% of all energy uses in residential building comes from lighting, motion sensor lights also have the potential to be there. Many other electronic equipment such as fans, tube lights, air conditioners can be interfaced with such sensors and can be switched off when not required. Fire detection system can prove to be an aid to help hospital follow the fire safety rules. The saline holder prototype can be further developed into a product which can be commercially exploited. Saline holder model can be used in the general ward where it is pretty hectic to monitor each and every patient. Thank you.
Any questions? Yes. Use the mic, yeah.
What will be the range of that MQ6 sensor? Because if a sensor is here and if any switchboard turns it, if it breaks out, then what will be the delay by that sensor to detect that fire if the distance is very large?
For MQ6, it is very small. For our project, we just made a small scale to just make our idea available for the audience. For a hospital, obviously, MQ6 won't work. We'll need a much bigger gas sensor.
Okay, then if there are no questions, thanks, Hetvi. So next we have the most awaited, I would say, a person who has traveled all the way from New York, the other part of the world, Professor Pramod Varshney from Syracuse University, USA. So before I call up him on stage, I would like to introduce him. So he received a BS degree in electrical engineering and computer science and MS and PhD degrees in electrical engineering from University of Illinois. And he has been with Syracuse University, New York since 1976, where he is currently a distinguished professor of electrical engineering and computer science and the director of CASE, which is Center for Advanced Systems and Engineering. He is also an adjunct professor of radiology at Upstate Medical University in New York. His current research areas are in distributed sensor networks and data fusion, detection and estimation theory, wireless communications, physical layer security, image processing and radar. He has published extensively. He is the author of Distributed Detection and the Data Fusion, published by Springer in 1997. He is a member of Tau Beta Pi and is the recipient of 1981 ASWE Dow Outstanding Young Faculty Award. He was elected to the grade of Fellow of IEEE in 1997 for his contributions in the area of distributed detection and data fusion. In 2000, he received the third Millennium Medal from the IEEE and Chancellor Citation for exceptional academic achievements at Syracuse University. He is the recipient of IEEE 2012 award. He received an honorary doctorate of engineering degree from Drexel University in 2014, distinguished ECE alumni from UIUC in 2015, and the Yaakov Bar Shalom Award for Lifetime Excellence in Information Fusion from ISIF in 2018. He is on the editorial board of Journal of Advances in Information Fusion. He was the president of International Society of the Information Fusion during 2001. Sir, it's great privilege to have you with us. I request you to deliver your keynote address.
Hello. So first of all, thank you for a very generous introduction. Second, I have to apologize for my voice. Somehow I left it on the plane, I guess, flying from New York to here. So I'll try my best, and hopefully I can last until the end. I hope you left enough time for me. The introduction was too long. So I will talk about information fusion, things that I've been working on for since 1981 actually. So, and it was before, even the term was known. I started working on it, as I said, in 81. The title, Six Blind Men, it will become clearer shortly as to what I mean by that. Okay, so these days we see sensors all around. And these sensors, like this smart city concept, you have, you can read basically in all sorts of fields. You have data coming in and you have sensors generating the data. And here, I guess, we will be thinking about healthcare-related things. So what is happening is that you have a lot of sensing that is going on, and these are different types of sensors that you have. These sensors provide information to a box that you can call data to decision processor, and ultimately, so this is where information fusion takes place. And ultimately, the decision is provided to a human, in this case, a medical doctor, who will try to use his or her own intuition, the information that has been fused, and some inference has been reached to the doctor, databases, tools such as IBM Watson, and so on. So basically, you have a lot of data that comes in, and how that can be used to reach smart decisions. That is what, basically we are hoping for and we are talking about. And actually, we need to get actionable information. So what sort of intervention is to be done, what sort of treatment, medication that needs to be done for the patient. Now the title. I'm sure you are all familiar with this story, but there was this poem by John Godfrey Sachs, that it was 6 men of Hindustan, that learning inclined, who went to see the elephant, and they were blind. In our case, the sensors are not blind, but they can see limited things, either within their geographical region or their capabilities that they have. They can sense blood pressure only and not something else. So basically then the thing is that each blind man came up with a part of the puzzle, a piece of the puzzle. The goal is that we want to combine this, fuse this, and come up with the fact that it is an elephant. So that is what the problem is all about, and that is where the title came from. That need for fusion through information being collected by relatively blind sensors, and actually these sensors are not talking to each other, so they are relatively mute also, but they can, and that would mean that there will be a collaborative decision making or some sort of a consensus kind of problem and so on. So then trying to define fusion, I mean basically theory, techniques, tools for exploiting synergy in the information acquired from multiple sources. These could be sensors, databases, humans, intelligence sources, you name it, whatever the source of information is, that you try to put it all together. Typical applications, detection, estimation, tracking, classification, that has been most of my life. That's what I have done. Then again, IoT was being mentioned, situational awareness for actuation and control. So, I mean, you can control things, you can do things. And this I added because this is the workshop for healthcare. And so trying to, I have the bottle. Hot water. It's a hot water, that's, thank you. I'll continue to drink, thanks. So, I mean, I worked on information fusion, as I said, since 1981, and lots of theory, but then there are many, many applications, and some of them I'm sort of showing a picture of. This leftmost one, there is no political statement that I'm making, but I'm just saying that we've been working on the problem of people crossing borders or whatever with the Army Research Lab. So we have been looking at sensing modalities such as acoustics, seismic sensors, and so on. And we had shown good results that we can classify whether it is a human walking or whether it is a human and a pony walking, etc., or a stray dog. So this technology we developed, 8 or 10 years ago. But as I said, there is no political statement here about border crossings. The application to biometric authentication, I hope you got my joke right. Okay. I didn't see any smiles or no reaction. Nuclear detection, so if we have some dirty nuclear material going, then using multiple counters, we can improve the detection performance. This was quite a revelation. It suddenly happened that we were able to apply our methodology to early diagnosis of Alzheimer's disease. Since it is health related, I'll spend a couple of minutes on it. And I also worked on something here which was vehicle health management, which is with NASA, trying to look at the health, because there's so many sensors in there, and we were able to obtain good results. So as far as the Alzheimer's disease thing is concerned, so what happens is that EEG is taken, and that way what you have is you have a lot of sensors, and then each sensor generates a time series, so it is a signal of this kind. And what people look for is neural synchrony. So that means this kind of thing, which means that if one thing there is action, and then if on the next sensor data also there is an action, then you try to characterize this neural synchrony. There is a baseline. Now if the neural synchrony is above that baseline, that indicates epilepsy. And if it is below, then it indicates Alzheimer's disease. So that's the kind of thing that we looked at. So I didn't want to sort of go here without showing equations and mathematics. Otherwise, you will feel cheated that he didn't do any math. So there is some math. And actually, I'll be talking about this at the Institute of Science tomorrow, much more details on this. So this is something that I've been working on for the last 10 or 12 years. And I'm using something called copular theory. And what it enables us to do is that if you have n random variables and you want to create a multivariate probability distribution out of that, then to make things easy, people assume independence among the random variables. Then the joint PDF is the product. But in most cases, in many cases, the random variables are not independent. So this theory, and then if you assume independence, you are losing out on information. So this gentleman, Sklar, he came up with this theorem that the joint cumulative distribution function can be represented, so there is a joint copular function. Let me go to the next thing. This really puts it together for you. This is easier to understand. So the joint PDF of your n random variables, dependent, can be written as the product of the marginal densities. With independence, this is where you stop. But based on Sklar's theorem, there is another term which is called the copular density, and this is the one that characterizes the dependence among the random variables. So this is quite a convenient form, the way it comes out, that if you assume the C to be 1, then you get independence. But if you have dependence, then what you need to do is from the data, so this is a data-driven method, that from the data you estimate the type of copula and the parameters of the copula. And that enables you to give a much better, much more accurate characterization of the joint distribution. So this is the key thing. And as I said, using this, we have done a number of things. So if one thing that you walk out with from this copular thing, this is what it is. I mean, this fact that this will enable you to do, use dependence in your analysis. There is a book by Nelson, and that's in 2013 also there is a next edition, and basically it's wonderful. So what you can do is the people have come up with different types of copular functions. So there is a library of copular functions. So you can pick the best one and find the estimates. I'm not going to be going into the details now, but that's what happens. Now, so this picture I think gives you the thing. So no, I mean usually what you have is you have symmetric kind of things, and you are not able to really represent skewed distributions. Copular theory allows you to do that. Your data is like this, but if you make this assumption, you're losing out. The model is wrong. The performance will not be as good as it could have been. So this picture should again remind you of the beauty of copulas, this ability, its capabilities, and so on. So the way we applied that, this was one of the bright graduate students, Satish Iyengar, and he finished in 2011. So this work was done 2010 or so. And the co-authors, Justin Dowells, he was a postdoc at MIT at that time. Now he's at NTU in Singapore. And Chihoki, he is a very famous signal processing person, and he was working in Japan. So the data that we used, you will see, that I'll talk about, is coming from Riken Institute in Japan. The measures, basically you want to quantify dependence or synchrony between multiple time series. I showed you those things in the beginning. One way to do that is by Granger causality. And one can do that, and in this, you assume independence. Another methodology, stochastic event synchrony, and this quantifies similarities between point processes. So again, this may be sounding Greek to you, I don't know, but these are all beautiful mathematical things. So one message that I want to give is, don't forget about fundamentals, mathematics and physics. I'm seeing people are getting too involved with the apps and everything, but not what is behind the apps, the math, the fundamentals. Please do not forget about them. So we used a copula theory, and we used something called multi-information. This is coming from information theory, as a global synchrony measure that summarizes the dependence structure. So this is the real data that we got from mild cognitive impaired MCI affected group of 25 people and a control group of 56 people. So we applied this methodology, meaning use of multi-information. So this is, you have heard of mutual information, so I of x, y. This is I of x1, x2, x3, x4. So multi-information is that. And basically, we were able to improve the classification performance from 82 to 85%. So, which was with using Granger causality under independence. So in the 80s range, 3% is a good improvement. So anyway, so this was one thing, health related, fusion related, and mathematics based. Okay, another important problem, health care related, which is, I guess, more elderlies are more prone to it. And I'm almost there, so I better work on these problems. One thing that I worked on, which I'm not showing, is something which is based on stochastic resonance. And that was something, it was a key plenary at Signal Processing Conference like a few years ago. So I talked about that other work. And it is online if you want to see it. So the point here is fault detection things. What happens is, maybe in a hospital, in a senior citizen place, you'll place lots of cameras and you will be sort of trying to monitor people. The problem there is that people want privacy. They don't want to be watched. So then is there something that you can do where people are more agreeable to use technology so that fault detection can be done there? So one of my brilliant colleagues, Sanam Velipsalar, she came up with this idea that instead of being watched, the person should wear a camera. So basically, the person, let's say if you put a camera here, and then you're walking around, so you are watching people, you are invading other people's privacy, but your own privacy is not being violated. So that's what she did, and that's what we did then. And then you are trying to decide if there is a fall, somebody is falling down or not. So the wearable camera is attached here. And so first you detect an event, sitting down, etc., and then deciding whether it's a fall event. So again, mathematics came in here. The threshold at which you decide fall or no fall, that is based on something called Ali-Silvi distance measures. So this is something that characterizes the distance between two probability density functions. So what you have is, you have an event fall and the complement no fall. So the threshold between that is being used based on one of the early Sylvie distance measures. And so that's the, so here are some example images. So this is the camera here, and this is from the indoor. So if a person is falling down, you see that you get frames like that. And this is some outdoor things. So buildings falling down in the sky. So these are the kinds of things, that's the data. And then using this, then we were able to, and so we were able to do that. And the topmost one is based on our methodology, meaning using the threshold which was computed using mathematical models, KL, divergence, and so on. And we were able to show that we had 94 and 90% accuracy, indoor and outdoor data set. So these are two examples that I thought I'll give, some things that I have been involved with for healthcare. There are other things, but like breast imaging, I worked on about 15, 20 years ago, etc. But these two, I think, convey the idea that there is the mathematics and sensor fusion can really result in some good results. Now let me just talk about lots of pictures and so on. So, I mean, these days, I mean, wireless networks, etc., they are everywhere, and more things are going wireless. So, I mean, you can just, you know what is going on, so I'm going to skip that. Then people have started working on wireless body sensor networks over the last 5 years. So then you have sensors of different kinds. You have sensors talking to themselves, talking to your laptops or whatever, robots and so on, and through the internet and so on. So this is just showing that there is a lot of communication, computation, and things going on, and one can do lots of things. The types of sensors, I mean, you name it, you can put them in necklace or wherever. I mean, so this picture I'll kind of move along, but it is just showing that imagination is there. I mean, you can let it go wild and say, okay, I'll put a sensor here, I'll put a sensor in my sock, my jacket will have a sensor, or many sensors, etc. So basically lots of sensors, they measure lots of different types of things. And again, that's the data that I was talking about, that you have to somehow use it to come up with your actionable information. I mean, you have data, so what? So the key thing is how to use it, how to come up with proper treatments, proper decisions, proper medication, etc. So that is something that's examples of sensors. I mean, people are coming up with lots of ways of putting them on a wrist, fabric, sock, etc. So it's just that lots of things are happening, and these are pictures from some recent publications. Okay, system architecture, I mean, I think I forgot, or maybe the slide didn't show up. One can do data fusion at different levels. It should have been there anyway. So, I mean, your data comes in, then you pre-process it, maybe filtering or whatever you want to do. Then one can do fusion at the signal level. So you get images, PET image and MRI image. So those images can be fused. So that would be at signal level or data level fusion. Next is feature extraction and feature level fusion. So these will be where you have multiple modalities that you cannot fuse directly. So then you take out some features and try to fuse those and come up with your decisions. Finally, decision level fusion. So the data from one sensor, you say, yes, there is a tumor. Data from another sensor, yes, there is a tumor. Third sensor, no, there is no tumor. You try to fuse these decisions and come up with, is there a tumor or not? So that is what different kinds of levels of fusion, and ultimately the output is some sort of inference, existence of a tumor or whatever. So that's the whole ball game, that you have lots of data available to you. How do you come up with the ultimate thing, yes or no, or classification, which disease? I put in just, how many minutes do I have? 10 minutes, wait, 5 minutes? I'll just keep on going then. So this is again, I mean, people are working on different types of applications, different types of case studies. So this one, April 2018, I thought, let me just put some pictures out of this. And the thing is that I am also one of those patients, one of the 8.5%. So the thing is that what can you do, how can you improve monitoring, etc. So people are looking at, again, this is a wristband kind of thing. One will measure different parameters, and then you will have these blood sugar, etc. And then machine learning will have to build personalized models, and then data sharing, which means that maybe you want to distribute that information on your social network maybe. So there are different layers, levels of things, and that's something that's going on. And then like this picture from the same paper, I mean, here you have all the buzzwords: 5G networks, clouds, IoT, smart clothing. So these are all buzzwords, but I mean, one can use all of these things, deep learning, machine learning, etc. So the point is that all the tools that are available there, you can use them to try to design systems for deployment at a large scale, small scale. It depends what the application is. Okay, I think I was going to skip security and privacy part, because this is something which is important. People can hack your, so pacemaker cases have been there. So the people have hacked the pacemaker, and there could be dire consequences. So that's an example. So you don't want people hacking, so what do you do about it? And then of course, you can falsify data, which is by hacking. Eavesdropping, maybe somebody listens to your information and uses it against you. I guess Hindi movies that you watch, I'm sure there's blackmailing going on, people find out, and etc., etc. So eavesdropping, there are problems, and denial of service, maybe you can just flood it with packets and the system doesn't function, etc. Privacy, again, the questions of who owns the data, who has access to the data, etc., etc. Can the doctor release the data to my wife, for example? There has to be a consent. So privacy, at what level, who is allowed to use it? And so there are lots of these issues that people are working on and should work on. Now some challenges for the future. So design of sensors, a lot of work is going on, and then people are looking for more accurate sensors, so you measure it better. You have to naturally calibrate the sensors, make them smaller. This is very important, energy efficiency. And this is something that has to be there, because if you are running it on a battery, you want to run it for a long time, not just every second day you have to replace the battery. So that is very important. Ergonomics, how to put them, place them, etc. So that is very important. That's a human issue that, if it is inconvenient, then I won't wear it. So that is important. Of course, cost and affordability. There was one question earlier about the cost of some system, 1 lakh or whatever. So again, if it's going to be expensive, then yes, maybe some rich people can use it. But if you have to get it to the masses, which is a large number, then it has to be affordable. Communication and computing infrastructure. So as we discussed, a lot of like volume, variety, and velocity of data. And if you have to do real-time requirements, there are some applications where, I mean, it doesn't matter if you get to know, like heart attack, that is time critical. So there is real-time requirement, but some cases, I mean, you can wait a day. So that's, again, some applications required that. If we are doing a lot of networking with body sensor networks, connectivity, coverage, availability, and security and privacy we talked about. So there are lots of these issues, open challenges for all of you to work on. Some of them maybe I'll work on too, but I'll mostly read your papers and your work. This is where I work, information processing and inference. So data deluge, as we just said. So then there need to be some good data compression algorithms. Compressed sensing, people have worked on since 2005 or 6. I have worked on it too, but again, not necessarily for healthcare. So again, one needs to see if there are applications. The data is the different modalities, blood sugar thing, temperature, your X-ray or whatever. So then how do you fuse them? There is data human generated, and that is uncertain. So is sensor data, but humans, we have a lot of biases, cognitive limitations, a lot of those. So then that needs to be taken into account when we are using human-generated data. So in my young age, I'm working with psychologists these days and trying to learn how humans think, what do we mean by cognitive limitations, and trying to use that in decision-making. So that's what young people do, learn new tricks. So we are trying to do, I'm trying to do that. So the data is incomplete, imprecise, uncertain. So once again, apps are nice. I'm sure people don't like my statement that I'm saying don't just limit to apps, go behind the scenes, but that is important. So the data is incomplete, imprecise, and uncertain. How do we model it? How do we take it into account? AI and ML-aided decision-making for healthcare, there is a lot that's going on. Now, this is extremely, extremely important. Cost and availability. So people in Bengaluru can use it, but then what about the outside of the city? So this has to be addressed. This next is trust in technology, acceptance and adoption. Do I trust the thing that I'm going to wear and it will give me an alert when there is, I don't know, if I have high sugar? So I need to trust the system, and then and only then I'll use it. This lack of education is important, and most of you do realize this. These two things I'll talk about in the next slide. This is also very dangerous. I'm just stopping at that. So I'll now give you some examples of some other things, and it will be parochial. There'll be a few Varshney's names appearing there, but they are doing good work on healthcare or related work, so I thought I'll talk about their work. First example that I'm almost done, 2 or 3 slides. So there is this person, Manish Bharadwaj and Bill Theis. These are 2009 MIT PhDs. And they, so I have met Manish. And then by the way, Bill, he's a MacArthur Genius Award winner, very, very prestigious award. So what they did, they wanted to do something, and they started a program, the DB program in Bihar, which is, as you know, rural, uneducated, poor, and so on. So what was happening was, first of all, people will say, yeah, there is something happening. So they won't even go to the doctor. Even if they went to their local doctor, sometimes they were not advised properly. Maybe sometimes they were. In government hospitals, I think free medication was available. So sometimes they were given, sometimes they were not. Let's say even if they had the medication with the instruction that this is a 7-day course. Third day, they start feeling better. They stop taking the medication. And then they become immune to that. The next time that this happens, they need the next layer of medication, etc. So you can see the struggle. So Manish, when I spoke to him, we chatted for 2 hours. This was maybe 2010 or something, or 11. And he said he wanted to create an infrastructure, a system where this does not happen. Again, I mean, you can only do so much. And he had to work with the doctors. They have to buy in. He has to work with social workers. They have to go to different villages and make sure things are happening, etc. So you can see the layers of bureaucracy, the kinds of things that has to happen. But I'm happy to say that the TB program, so what he did was very simple device, a pill box. And then if like Monday through Sunday, whatever, if Monday the thing opens, there is a signal that goes to some place that it was opened. It doesn't mean the pill was eaten, but this is the simple thing. So then if the 4th day the signal is there that the person didn't eat, then maybe a social worker will go and say, "Kya hua? Kyun nahi khaya?" etc. That kind of thing. Then maybe they will encourage, and then they will start eating again, etc. So there is a lot of intervention, a lot of social stuff that needs to be done. But I just read in his latest report that the catchment now, they started with this much, is 2.5 million. So they have made a dent, and he's doing well. So I mean, I think he spent at least many years on the ground in Bihar rather than working for some he's a communications PhD, Greg Warnell student, if you know. So anyway, the thing is that he devoted his life to this. The second thing I'll talk about, IBM has a Science for Social Good program. And these 2 people, it is the brainchild of these 2 people. And again, I said that this name will show up, so it is showing up. He's one of my sons. He is passionate about society and social good. And so both of these, they really worked on things very hard, and finally IBM bought into it, and they're spending money, resources. And they have many, many projects going on. If you are interested in learning more about it, actually Daya Prasad Kulkarni, he has to coach about seeing Arogya Seva, if they can somehow work together. The idea here is use of artificial intelligence, machine learning, data analytics, all the new tools to apply that to energy, healthcare, education, innovation, all of these societal problems. They can work with people, NGOs, and so on. So if you're interested, go to search for this, and you'll find it, a lot of things. One project that's directly related, childhood diarrhea. 500,000 children die globally per year. For this, oral rehydration, salts and zinc combination is inexpensive and is most effective. They use data from Nigeria, but I'm sure the same problem is here. That, I mean, it's known, but when the person goes to the medicine shop, this is what happens. They say, "Oh, why this? This is a better one," even though it will not work, but it brings in more money. So wrong advice, more expensive thing is given, that is not as effective, but then that's how the system is. So one has to really work hard, society, technology, whatever. So technology is there, but people are not using it, advising. Okay, so that's one example. The third thing, one is the use of AI and machine learning. So, another Varshney shows up there. This is my other son. So he used to be at IBM, and he created Chef Watson. So in case you are interested in knowing what it was, 2013 or 14, just search for that, and you will find, articles in Time magazine and also IEEE spectrum, and lots of places. So the idea here was that computational creativity, trying to generate new recipes that had never been done before. And anyway, so the goal here is that one can actually try to use it. That was one of his goals, recipes for healthy yet tasty dishes. So people, if it is healthy, people say, it will not taste good. So how to make them tasty? And IBM actually had an app until recently it was available. But he left in 2013, then it sort of died at IBM, but it was quite a path-breaking thing. Another problem that is obesity surveillance. And so again, they work, this is an undergrad student, and based on data analytics and location information, they found areas that with lower obesity meant people talk to each other more. And so basically, if you are interacting with people, you eat better and you are not obese. So for whatever that is worth. So my final comments, that one needs to really look at the problem in a very large-scale way. It's a socio-technical system. Social side, there are humans, there are organizations, government, whatever. On this side, hardware, software, etc. And what is it that you need to do? By ourselves, we cannot solve the whole thing, but we can take small pieces of it. But when we do that, then we need to kind of know that there are other parts also. So if we are doing socio-technical aware systems, meaning knowing that it will be used by society or people will not use it, then what do you do, etc. So the point is that it's not just technology, but there is a lot more to do. So I'll stop here, and thank you for the invitation.
So before we break for tea break, we have questions for Professor Varshney. Okay, so maybe he's available for some more time.
I'll be here all day.
Yeah, he's there, and even in the break you can interact with him. But before we close this session, but I would like to acknowledge our sponsors, INAXIL, IEEE Humanitarians Activity Committee, and also Arogya Seva, who have specifically sponsored this session of NetHealth. And Arogya Seva actually flew him from US to here. Thanks to that, Dr. Daya is not there, but his representative there. And people who were there in the conference for a couple of days, you would have seen their booth also, which was really amazing. So with that, I would like to invite Rohan to join me in thanking Professor Varshney. Or maybe that side. Thank you. We'll have a quick tea break. So by 11:20, we'll be back for the next session. We have one more keynote to start with. Thank you.